Okay, so this is a recording for a lesson that I want to give for what day is it going to be? It's going to be the 11th of December on energy. Sorry I can't be there today, guys. We had some sickness going on in my family in the middle of the night here, so I'm gonna record a video lesson right now. This shouldn't take long. It's not going to be a very long lesson. It's actually a review of Science 10, and that's actually one of the first things I'd like you to do. Is if you haven't had a chance to either get this printed off for you or print it off yourself. Right here, I believe this is showing up nice. And on my website, I put up a grade 10 physics practice test. And what I'd like you to do, ideally, is take about the first half hour, 45 minutes of class, probably more like half hour, and see whether you can solve these questions. The basis of this energy in it is actually very similar to what you've done in Science 10, or at least what you should have done in Science 10. I know it's been a while for some of you since you've been there. I just want to give you guys just a quick review though before you do that, just in case you're like, oh my goodness, it's been forever since we did Science 10. But basically, there's two formulas I want you to know. So make sure you get a hold of this physics practice test because that's ultimately what I want you to practice today. Let me talk a bit about energy then. There's a couple main forms of energy I want you guys to know about. One of the forms is potential energy, and the other form is kinetic energy. And if you've heard these terms before, you'll kind of know intuitively what they mean. Potential energy is energy that hasn't been used yet and still can be used. And kinetic energy is energy that is already in motion, that's already doing something. So there are two formulas basically that I want you to know then. One is the kinetic energy formula, which you should have learned these in grade 10 science. So if you recall them, that's fantastic. If you don't, that's not probably the end of the world either. They're on your data sheet and they're very straightforward. To find out how much energy an object in motion has, which is kinetic energy, you need 1/2 of its mass and its velocity squared. Another type of energy you could figure out is gravitational potential energy. And to find out how you calculate this energy, you just need mass times g, which will be 9.81. I just want to put a little note in here for you for that. G will be 9.81. I don't have my little stylus tablet here, so I'm doing this with a mouse, so you have to bear with me. I won't be able to do nearly as much stuff as I normally do. Units are important. You have to have mass in kilograms for sure. Height needs to be in meters. If you're using velocity, it has to be in meters per second. In terms of resultant units, energy then is based on something called a joule. Joule. Named after a famous scientist, of course. A joule is equal to a couple different things. Basically, you could call a joule equal to a kilogram times a meter per second squared times a meter. So often we sometimes say that a joule is equal to a kilogram meters squared over seconds squared. If you were to look at like the mass times velocity, mass is kilograms, and then velocity would be meters per second, so then you'd be squaring that as well. So, but preferably we just use capital J. So what I'd like for you guys to basically do then is try this practice test. I'm going to try to send along an answer key if I can, and I'd like to see whether you guys remember how to do any of this from grade 10. I know a few of you guys were in my grade 10 class. These are questions directly off my grade 10 assessments. So take a little while to try those. I have some more examples here that, to be honest, I think you guys can figure it on your own. I don't think you need me for this. This is very much just a plug these numbers into a formula. There is one new formula I do need you to know about, though, that's on your data sheet. You might be wondering, well, there's one more energy formula on there, and it's this one here. It's energy potential is 1/2 kx. And as soon as you see k and x, hopefully you think, well, hang on, we've done that before. Those are springs. Springs. And I like to imagine like a slingshot, so that's the example I have at the bottom of this one right here. You've got a slingshot with a constant of 156 newton meters, and it's pulled back 1.68 centimeters. So don't forget to make that 0.068 meters. Have to have that unit be in meters. And so, I mean, for this formula here, you'd just make this your 0.068, and that would be your meters would be squared, and then that k value would have been 156. And that would tell you how much energy potentially like a slingshot has, or anything that has elastic properties. Okay. That was not a formula you probably would have learned in grade 10, so I didn't put anything like that on the assessments. So here are some examples to try if you'd like to. One last thought here. You also should have learned a formula about work in grade 10. And work is basically the same thing as energy. Their definitions are similar to each other. So energy is defined as the ability to do work. You need to have energy in order to actually be productive. Work is known as a force through a displacement. And so this is also a formula that I hope is familiar to you, even if it's been a while. Work is equal to force times distance. If I talk through a couple of examples here, first on here, if a student is just sitting in their desk writing a test, how much work is done? These two are trick questions, by the way. There is no work done. If you're just sitting there in your desk, you're not actually moving any distance. You actually have to move a distance. Maybe you could argue, well, you're moving your pencil back and forth, and so I'd say, well, yeah, then okay, however much force you're putting on your pencil times however much distance your pencil moves, that's a force. But if you're not actually moving, there's no work. One more thought here. I wish I had my stylus, so I'm going to draw this as nicely as I can, but bear with me. Imagine that there's you, and then on your back is a backpack. That's not horrible. And you wear your heavy backpack full of physics homework, and you walk down the hallway. Well, the force that you would be applying would be basically like gravity is pulling things down, right? And so the force that you would be applying, your applied force, would be applying it in like the upwards direction. You're basically keeping the backpack from hitting the ground. Okay. So your force is going up. I guess that's what I'm trying to hint at here. If you walk down the hallway this way, your displacement or your distance is not in the same direction as the force. And your force and your direction have to be going the same way. Otherwise, it also doesn't count as work. And so in this particular example here, you would get credit for work from lifting your backpack from the ground this distance up to your shoulders. That would count as some work because the applied force up and the distance up are in the same plane. But if you have enough applied force up but the distance is going like perpendicular to it, that doesn't count as work either. Which leads to this formula, and this is the one that's actually on your data sheet. In grade 10 you probably would have learned, I say probably because it depends. I know a couple of you, though, were in my physics class, so I know for sure I taught you this. Work is force times distance. But the trick to it is sometimes we throw in a little cosine theta because it depends on whether or not the actual work is in the same direction, whether the force is in the same direction as the distance. So like imagine that you are pulling up on a block along this angle right here. Using like a trigonometry type triangle, you could say, well, the actual force that was applied in the actual x direction would only be the cosine of that force. Like if this number right here is 25, then this number right here, let's give an angle to, let's say this was 12 degrees. Then the actual force that gets applied in the same direction as your distance would be 25 cosine of 12. Okay, so big note here. Force and distance must be in the same direction. So I've got an example here. Just of how like a box might get pulled here. I hope this makes sense here. Here's where the box originally was, the dotted lines here, and someone's pulling at an angle of 30 degrees. Well, this force was actually getting applied at like an angle, so you'd actually have to use that F times the cosine of 30, and then still multiply by the distance as to how far it was pulled. That's how much work was actually done. I've got some examples here. I think I will just leave this for you guys, though. Well, actually, no, let's not. I won't leave them for you guys. I may as well do them. Work is equal to force times distance. If you need the cosine part, use the cosine part. If there is no angle, if it's cosine 0, hopefully my grade 12s here will know this. Cosine of 0 is actually equal to 1. So like if there is no angle, you don't really even need this section here. So to find the work done here, this would be 8.1 newtons multiplied by 2.3 meters. I don't have a calculator nearby, so you guys will have to be able to handle that on your own. The actual mass of the object right here is completely irrelevant. That was just thrown in there just to mess you up. So whatever 8.1 times 2.3 is, so I don't know, probably about 17 joules. For this one right here, the only difference is now we actually need that 35. So take your 76 newtons times by your distance of 12.7 meters. But now the actual angle was above the horizon, so you need the cosine of 35. To be honest, this is really straightforward. It's basically just take numbers in and plug them in. We'll actually do something more complicated next week with this, but for the most part, I'm hoping this is kind of review. One last thought: if we give you a graph, because we have done lots of graphs in the past, if you guys remember about doing area underneath a graph, the area of a graph, like if I give you a box along these lines here, area is normally length times width. But the length of your box here would be a force, and the width of the box would be a distance. So if you found the area of a box, that would actually be your force times your distance. That would be how much work you did. And work is basically the same thing as energy. Work and energy are synonymous with each other. So if you do work, you used energy. If you use energy, it must mean that you're doing some sort of work. So you could actually calculate how much energy was spent by looking at a graph. And so I've got one example here. My question is how much work was done, and maybe I might even phrase this differently. I might say how much energy was used. So you could use work and energy interchangeably. It's called the work-energy theorem. I think I had a slide on it somewhere. Let me just double check. Maybe I don't. Oh yeah, I did. So work-energy theorem. So energy is work, basically. For those of you in my grade 10 science class, I know there's a few of you in there. I said that the change in energy is equal to work. I believe I had a formula like that for you guys there. So if you ever have work, you also have energy. So, anyways, for this last example here, what's the area under this graph? Well, I'd say this graph seems to go according to a triangle. So that would be 1/2 base height. That's your area. The base looks like it's about 110 meters. And your height looks like it's about, what is that, 160,000 newtons? That. So again, I don't have my calculator with me, but if you do 1/2 of 110, because that's the distance along the bottom here, and then the actual height of the graph is 1600, the area here of this shape would be how much energy was spent or how much work was done. So, very, very simple first day then. Basically, my goal for you guys is I'd like for you to try this grade 10 practice test here. So hopefully this is showing up when I open it up on my screen here. But there are, I believe, 17 questions. 17 questions. And I'd like you guys to give those a try. If I can, I'll send an answer key. If not, we'll go over them tomorrow as a group and see whether you guys are able to solve these. So I guess the twist for some of them is sometimes you plug in your numbers and you just find energy. For example, here's a different one though. If you can see this one, number 2. If I give you mass and I give you energy, can you find one of the other variables? So that just requires algebra. You just have to be able to rearrange these things. So anyways, I hope things go well. Sorry I can't be there today. I should be back tomorrow though. Like I said, we were having some sickness in the family. So we'll talk to you guys tomorrow. Hopefully this works.